the electric field equation as capital E equal to K Q divided by R square. So we have our E minus Q and E plus Q. So to find out the net electric field, we only have to add them together. If a dipole, this is along the axial point and this is along the equatorial point. So due to a positive charge, the electric field was pointed outwards, and due to a negative charge, the electric field lines were pointed inwards. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, Mysuru, the Temple of Excellence. In the previous class, we were discussing about electric fields. So let's see what electric fields actually mean. Okay, it was actually told that electric field represented by the letter E. So if there was a positive charge Q, let's say this is a positive charge Q placed in space, then there will be a region around which the influence of this charge is felt. And if we bring a test charge into that space, let's say we bring a positive test charge to that space, then this charge will experience a force, and that is known as electric field. So we can say that electric field is equal to force experienced by this unit charge, or force experienced per unit charge. So what does this actually mean? We know that if there are two charges, we can calculate the force using Coulomb's law, which just means that F is equal to K Q1 Q2 divided by R square. So let's say this is the distance between them and this is denoted by R. Then the direction will be indicated by the unit vector R caps. R caps will be the unit vector indicating the direction. So let's keep all that aside. The important thing we have to focus here on is that this is the equation denoting Coulomb's law for this charged particle. That is, capital Q is the charge we placed, which is exerting the electric field, and small q is the test charge, which just means that it is the unit charge which is kept at a distance r from it. So it will experience a force, and that force is found out through Coulomb's law, and that is this equation. So, and R caps will denote the direction. So we can write this as K Q small q divided by R square and the initial q that was already there. So you can see that the q's cancel each other out, and we can simply write it as K Q divided by R square, which is the equation for electric field. So we can write the electric field equation as capital E equal to K Q divided by R square. So this is the equation denoting electric field. And the another equation is the definition itself, that is F by Q is equal to E, which just means that the electric field is nothing but the force experienced by a unit test charge placed at a point. Where exactly? That is, if we place a charge like this and we bring a unit positive charge, this unit test charge will experience a force. This will be experienced only under a region under which this charge can exert its influence, and that is known as electric field. Now, what if there are not just one charges, but instead there are multiple charges? Let's say there is a Q1 here, a Q2 here, and a Q3 here. And what will be the electric field at this point, which is P? Okay, this will be R1P. And this distance will be R3P. And this distance, let it be R2P. So this is the distances from each of these charges, and we want to calculate what will be the electric field at that particular point. So let this be a positive charge, this be a negative charge, and this be a negative charge. So we know that positive charges, the field will be directed outwards. So the positive charge, the field will be directed outwards, and let this be E1. And for Q3, it will be directed inwards. So it will be directed inwards. So that is known as field E3. Electric field component will be E3. And for similarly for Q2, it will be simply E2. So there are three components acting. That is, one will be along the direction because it is a positive charge. One will be in this direction and the other one will be in this direction. So this is the electric field vectors. So what we have to do now is we have to find what is the total electric field experienced at the point P. So what all details we have? We know which are the charges, we know what is the distance between them, and we know what is the electric field exerted. Just like how we have used superposition principle before, we are also going to use the principle of superposition here again. Instead of force, we are going to calculate electric field. So here the net electric field E net will be equal to the total number of, the vector sum of all electric fields, that is E1 plus E2 plus E3. So this will be the total electric field, and we know what E1 is. The electric field, the equation for the electric field is given by E is equal to K Q divided by R square. Instead of capital Q, we have small q here, and K is nothing but 1 by 4 pi epsilon naught. For simplicity purposes, I'll just take it as K. So we can write it as K Q1 divided by R1P square plus K Q2 divided by R2P square, and finally K Q3 divided by R3P square. And if there are n number of charges, we can just say that etc. up to plus K Q N divided by R NP square if there are n number of charges. So now we only have 3 charges, and if you look here, we have K as common factor in all of this, and K is nothing but 1 by 4 pi epsilon naught. So E net is equal to, we'll take the K out, which is nothing but 1 by 4 pi epsilon naught, and then the remaining things are put in a bracket, that is Q1 by R1P square plus Q2 by R2P square and Q3 by R3P square. And similarly, if there are n number of charges, we'll continue that up to Qn divided by Rnp square if we are talking about a general case. And then we can write it as 1 by 4 pi epsilon naught summation over, that is the sum of all these charges, I is equal to 1 to n Qn divided by Rnp square. So this will give the total electric field of a system, and this is found using the superposition principle. So we used it to find the total amount of force exerted by a system of charges. Now we are using the same principle to find out the total amount of electric field exerted by a system of charges at a particular region. So this is very similar to what we did in the previous class. So I hope you have understood what electric field is and how to calculate electric field of a system of charges. And we were discussing about dipoles. Dipoles are nothing but two charges equal in magnitude but opposite in polarity separated by a distance of 2a, which is half of this distance is a, the other half is a again, so 2a distance. So one charge will be positive q, the other charge will be negative q, but the magnitude will be same. So this is known as a dipole. And how can you create a dipole? It's fairly easy. If you have two metal spheres, let's say this is two metal spheres that is in contact with each other, and we bring, let's say, a positive rod near this, then again, as we discussed earlier, there will be charge separation here, and one charge will be concentrated on the other side. And if we separate this spheres, keeping this glass rod like this only, then we will have two metal spheres of one being negatively charged and the other being positively charged. And these charges will be equal in magnitude, but they are opposite in polarity. So we can say that the distance between, let's say, this charge and this charge is 2a. And now we have created a dipole. Just like that, we can create dipoles. So we are going to learn what are the specialities of a dipole. Is this dipoles existing in nature? For example, water molecule is actually a polarized molecule. Under the right conditions, it can develop polarity. That is, it has a positive and negative charge. When the charge centers, let's say positive and negative, do not coincide and they are separated, then we can say there is a polarity. And when the distance between them is of, let's say, 2a, and that is known as a dipole. So we are going to mathematically find what is the relevance of a dipole in connection with an electric field. So in order for that, we are going to consider a dipole, let's say, plus q and minus q, the distance between them being 2a. If it is a positive charge, then the electric field lines will be pointing outwards, and if it is a negative charge, then the electric field lines will be pointing inwards. We already know that. And we also know that there is an electric field around this particle. So there will be electric fields around charged particles. And if we place a test charge or we take a point here P, we know that the electric field will be equal to K Q divided by R square. Similarly, the negative charge also will be there. If it is positive, the sign will be positive. If negative, then the sign will be negative, which just indicate that if it is positive, it is going outwards, and if it is negative, then the field lines are converging inwards. So my question is, if the electric field of a given charged particle is like this, what will be the electric field of a dipole? Let's say, what will be the electric field at point P? Or let's say, what will be the electric field at point P? Will they be similar? Will they be different? Or is it even relevant? Will they be zero? We don't know for sure, right? We are going to prove that, or we are going to find out that will the electric field experienced at point P1 and P2, is it going to be similar, and is the equations going to be similar? Will there be any change in the equation? Because these are a set of charges equal in magnitude but opposite in direction. Equal in magnitude just means that if this is plus 2, this will be minus 2. Only the signs will change, but everything else will be remaining the same. So to prove this, we are going to take one point here, P1, and one point here, P2, and we are going to calculate the electric field at point P1 and P2, and we are going to find out what are the differences and what are the specialities. So let's get on to it. So for that, first we are going to consider a particle, a dipole, that is minus q and plus q. So this is a dipole which is equal in magnitude but opposite in polarity, and the distance between these 2 points is 2a. So this will be 2a. So the total distance between the two charged particles or the length of the dipole is determined as 2a, and we are going to consider a point P which is r distance, let's say, which is r distance away from the center of the dipole. Why we are taking r distance away from the center of the dipole itself? So that we can make our calculations much more easier. So we are going to take this distance as r, and we know that there will be electric field present at the point P due to the presence of a positive charge and due to the presence of a negative charge. So we are going to find out if there is any difference of electric field at point P due to a single charge and due to a dipole. So we already know the electric field is given by the equation E is equal to KQ divided by R square. So this is for a single particle. But now we have a dipole. So what will be the difference? Let's calculate that. So first we know that E is equal to KQ divided by R square. But here the distance from this point to point P is not R square, but rather it is just, here the distance is K positive Q divided by, so this is A and this distance is A. So this is actually R minus A square. Why? Because the total distance is R and we only need the distance from positive Q to P. So we have R minus A whole square. So instead of R, we have R minus A because we only need this distance, that is from positive Q to the point P, and that is R minus A all square because of the equation we have found out earlier. And that, let us put that as 1. And we know that the sign is positive because since this is a positive charge, this will be the direction of the electric field. And for a negative electric field, we know that positive charges radiate electric field outwards while negative charges radiate electric field inwards. So this will be the direction of electric field of the negative particle. So we know that the negative particle's electric field will be in that direction. And this is E due to positive Q, and electric field due to negative Q is given by K, Q, negative sign indicates the direction of the electric field and it is noted here, divided by, now what will be the distance? Now we know that the distance is 2a. Now we want the distance from here to here. So we know that the distance from point P to the center is R. So from this point, we are again traveling a distance more to reach the negative charged particles, which is minus Q. So we know that this is R plus A. So this is the total distance, and then our equation transforms to R plus A whole square. So this is our equation 2. So we have our E minus Q and E plus Q. So to find out the net electric field, we only have to add them together. So to find out E net at point P, we have to find out E plus Q plus E minus Q. So we are going to find out what this actually means. So we are going to add these two equations together. So we'll get E net as, E net will be equal to K positive Q divided by R plus A square minus, because E2 or E minus Q is given by minus KQ divided by R minus A whole square, because the direction of the electric field is in the opposite direction. So we'll get KQ divided by R minus A whole square, and this will be the equation. So on adding these two together, we'll get, that is, KQ will be common in both equations. So we'll take that out, and then the remaining will be R plus A whole square minus 1 by R minus A whole square. So we'll have to cross multiply this, which just means that KQ into R minus A whole square minus R plus A whole square divided by R plus A whole square into R minus A whole square. So this equation is actually in the form of A square minus B square. And converting that and simplifying it, we can actually solve it as E is equal to KQ into 4AR divided by R square minus A square the whole square. So now we have this equation which we can rewrite it as, we can expand K. So this is net electric field at point P, and we can rewrite it as E net is equal to 1 by 4 pi epsilon naught Q into 4AR divided by R square minus A square the whole square. So just because you see a 4 here and here, don't go and cancel it. You have to keep it there. We have a use for it. For you to cancel, I'll give you something else. So what we can actually do is that we can assume that here A is much lesser than R. We are considering that the dipole we have taken, which is positive Q and negative Q, having a distance of 2A, and we considered a point P at R distance away from the center. So we are saying that this distance A is negligibly small compared to this large distance R. So if we assume that it is like that, then we can assume that A square is almost 0. Then we can rewrite this equation as E net is equal to 1 by 4 pi epsilon naught, or simply K, into 4QAR. So 4QAR divided by R square the whole square. So our equation will get transformed into this form. So I'll just write it up here. That is E net is equal to 1 by 4 pi epsilon naught into 4QAR divided by R raised to 4. So we can cancel out these two R's, and this R and this R will cancel out too. So you can rewrite this as 1 by 4 pi epsilon naught 4QA divided by RQ. You can actually write this as 1 by 4 pi epsilon naught. I'm writing the 4 as 2 into QA divided by RQ. So we know that 2 into QA is nothing but the dipole moment we actually found out earlier. So we know that P is actually equal to 2QA. So this is the dipole moment of this particular dipole, and the direction of the dipole moment is from negative Q to positive Q. So we can substitute this P in this place. So actually we can write it as E net is equal to 1 by 4 pi epsilon naught 2P divided by RQ. So this will be the final equation. So the net electric field at point P, that is, this is known as the axial point. Okay. When we are taking a distance P along this line, let's say in this direction or in that direction, it doesn't matter. If we are taking in anywhere in this direction, that is along a straight line, then this is known as an axial point. So we have found out that if we take a point P in the axial direction at r distance away from a dipole center, then we'll get the electric field as 1 by 4 pi epsilon 0, or simply just K, into 2P divided by r cube. So what does this actually mean? E is equal to electric field at an axial point will be equal to 2P K into 2P divided by r cube. This is the thing we have found out. So we already found out what the electric field is due to a point particle, or just a simply charged particle, and that is given as KQ divided by r square. So what are the comparisons we can make from these two? We know that the electric field will be reducing as the square as we go along with the distance. So if we are here and we move from this point to this point, the electric field will actually decrease by a factor of the distance squared. But in this case, for a dipole, if we move the same distance, then let's say distance of r, then the electric field will diminish as the cube of that distance. So that is the one main thing we have to note from this equation. So to simply summarize it up, what we did was actually we considered a dipole and we considered a point P r distance away from the center of the dipole, and the total distance of the dipole is nothing but 2a. From this, we know that E due to plus q and E due to minus q is nothing but kq divided by r minus a whole square, and due to minus q is nothing but negative sign because the electric field's direction is in the opposite direction. So negative kq divided by r plus a the whole square. And we know that to get the net electric field, we have to add these two electric fields together, which we did. And then we got the net electric field as E plus Q plus E minus Q, which is nothing but K and Q are common. We took that out. And finally, 1 by R plus A whole square minus 1 by R minus A the whole square. So this was the equation we got. We simplified that and we got the final result as E is equal to K into 4AR divided by R square minus A square the whole square. And we considered the fact that R will be very larger than A, or A will be very less than R. Then it implied that electric field will be equal to 4AR into K divided by R raised to 4. And these two R's were cancelled and we got the final equation as E is equal to, there was a Q here. We forgot to add the Q from KQ. So 4ARQ divided by R square minus A square the whole square. And we considered that R is very greater than A. Then we can say that E is equal to 4ARQ into K divided by R raised to 4. The R and R got cancelled. And finally, we can write it as E is equal to 4AQ divided by R cube, and there is the constant of proportionality K, which is nothing but 1 by 4 pi epsilon naught. And we wrote this as 2 into A into Q into 2 divided by R cube. And there was a K here. So we wrote this as K into 2P divided by R cube. So this was our final equation, which we have written as E is equal to 2P K divided by R cube. So this is the equation for an electric field which is situated along the axial points, which is that either in this direction or in this direction of a dipole. So if it is situated here or anywhere along that diagonal, we'll say that this is the equation for the electric field. Now the question arises, what if it is not along the axial points? What if it is somewhere along the vertical component? So that is known as equatorial points. So that is known as equatorial plane. So the electric field along the equatorial plane. Now we are going to find out what happens when the point is along the equatorial plane. Equatorial plane means what if it is along the vertical direction. So if we take this to be a dipole, so first we'll consider that this distance is r. So first we'll consider that from the center of the dipole to the point P, the distance is r. So that this distance is a and a. So the dipole is equally divided. So we can say that now we can say that r is the distance from the center of the dipole to the point P. If this is the case, then we can say that there is an angle theta here, and here it is 90 degrees because it is perfectly at the center and it is normal to the dipole. So we can say that this angles are 90 degrees, and we know that this is r and this is a. So obviously we can find out what is the distance between positive q to P. So why do we have to find the exact point from Q to this P? Why can't we just take this direction? That is because we are calculating the electric field from charge Q to point P. We cannot travel in this direction and then straight up. We have to know what is the distance from positive Q to this point, and similarly we have to know what is the distance from negative Q to this point P. So lucky for us, both distance will be same. Here in this case, the trusty Pythagorean theorem, which states that if we have a right angle triangle, base square plus altitude square will give you hypotenuse square. So if this is A and this is B, A square plus B square will give you C square. So just like this, we can find out what is the distance from positive Q to P, and that will be given by base square plus altitude square, which is nothing but A square plus R square. So hypotenuse square will be given by A square plus R square, but we have to simplify that. We don't need hypotenuse square. We actually only need hypotenuse, the length of the hypotenuse. So what do we have to do? We have to take the root of that. So in order to find out the hypotenuse, it will be A square, that is base square, plus altitude square, that is R square. But we don't need the square of the hypotenuse. We only need the hypotenuse's length. So we have to take the root of that. So that is denoted by all raised to 1 by 2. So if you have any quantity that is root of something, you can denote it as that quantity raised to 1 by 2. So that is the only thing we have been doing here. So we found the distance from positive Q to P, that is A square plus R square whole raised to half. So we know that this distance is nothing but R square plus A square whole raised to 1 by 2, or A square plus R square whole raised to 1 by 2. It doesn't matter because it's positive. And then again, the next thing that is coming into play is that the direction of the electric field. So we know that since this is positively charged, the directions of the field lines will be directly outwards. So the field lines will be going in this direction. So we'll mark this as E1. And we know that the electric field due to a negative charge will be, or the field lines will be directed inwards, so that the electric field will be coming in this direction. So this will be the actual representation of the field lines due to positive charge Q and negative charge minus Q. So in order to resolve the positive component, that is E plus Q, we can say that this E plus Q can be resolved as E cos theta and as vertical component, that is E sin theta. So we can resolve E plus Q as E cos theta and E sin theta. And similarly, for the negative Q also, we can resolve it as E cos theta, negative Q, and E sin theta. So as you can clearly see here, that this will be E sin theta due to positive Q, and this will be E sin theta due to negative Q. So this will be the vertical components, that is E sin theta and E sin theta due to negative Q and positive Q are vertically in opposite direction, so that these components actually cancel each other out. So these vertical components will cancel each other out, and what is remaining? Both of the cos components are along this direction, that is E cos theta due to positive Q plus E cos theta due to negative Q are both in this direction. So both of them add up. I know this might be getting slightly confusing, so let me explain it just one more time. So first, we are considering a dipole, that is plus Q and minus Q, and we are taking a point at the equatorial plane. Let's say this is a point P along the equatorial plane, and the distance from the center of the dipole to that particular point P is denoted by R. Then we can say that the distance from Q to P is given by the base of the squared plus altitude squared, that is using Pythagoras theorem. And we know that this distance is A and this distance is A, and we also know that this is a right angle triangle, so that we can add base square plus altitude square to get this distance, which we found out to be R square plus A square whole raised to 1 by 2. So we found out this distance, and we need this distance so that this is the line along which the electric field lines will be passing through. So we are going to find out what is the electric field at point P. In order to find that out, we need this distance, and we know that the electric field lines will be passing through that point. Let's say this is the dipole. Then the electric field lines at point P will be passing through like this due to plus Q, and the electric field line due to minus Q will be passing through like this. And since these are two vector lines, we can actually resolve them into their components. And while doing that, we'll just take this top part and we'll just bring it here. So it will look something like this. So we are going to resolve it into X and Y components. And while doing that, this is due to plus Q and this is due to minus Q. While doing that, this is the Y axis, and along the Y axis, due to E plus Q, it will be E sin theta, and here it will be E minus sin theta or E sin theta due to negative Q, and this will be due to positive Q, and the cos components will be along this diagonal, that is E cos theta due to positive Q and E cos theta due to negative Q. So we can clearly see that the directions are same. So if E cos theta due to plus Q is in this direction, E cos theta due to minus Q is also in this direction. So these two components add up, while the direction of E sin theta due to plus Q is in the upward direction. E sin theta of negative Q is actually in the opposite direction. So these two components cancel each other out, and the only thing remaining is E cos theta due to positive Q and E cos theta due to negative Q, which adds up together, that is E cos theta plus E cos theta. So this will be obtained here. So why do we need this and how did we get this? So since there are two vectors, vector due to E plus Q and E minus Q, we took the resultant and we solved it into its component elements and we simplified that, so the electric field at that particular point E will be given as this form. So we know that the electric field at point P will be equal to 2E cos theta. Now the equation is not over. We have to substitute this in the given formula. So we know that the total net E or net electric field at point P will be given by adding these two components together. Let's call E cos theta due to plus Q as E1 cos theta and E cos theta due to negative Q as E2 cos theta for simplicity purposes. So we can say that the net electric field at point P due to E cos theta of plus Q plus E cos theta of minus Q can be written as E1 cos theta plus E2 cos theta. So this will be the net electric field that is experienced by point P. Okay, how did we get this? We resolved plus Q and minus Q into its components and we cancelled out the vertical components because they were in opposite direction, and we added up the x components because they were lying in the same direction. As you can see here, negative charges inward direction, positive charges, the electric field lines will be in the outward direction. So we resolved it and we got this equation. Now we only have one equation, but this is not a clear-cut form. So we are going to simplify this even more and find out what the exact answer to this is. So as you can clearly see here, cos theta is common here. So we are going to take cos theta outside this so that we can write E1 plus E2 into cos theta will be the net electric field. Now we know that the definition of cos theta is equal to adjacent side divided by hypotenuse. So what is the adjacent side here? The adjacent side is simply A. If this is theta, then the adjacent side is A. One more thing to bear in mind, if this is theta, then one more thing to bear in mind is that this angle will also be theta. These two angles will be same. So you don't have any confusion where cos theta came from. If this angle is theta, the electric field will be in this direction, and when we solve this as its y component and x component, then theta will be here. So you don't have any confusion with that. Okay, so E1 plus E2 cos theta, and cos theta is nothing but adjacent side by hypotenuse. So the adjacent side here is nothing but A. Why? Because R is exactly coming from the center, so it divides the dipole as two equal parts. That is, the length of the dipole is 2A. So since it is divided equally, one side will be A and the other side will be A. So we can say that it is equal to E1 plus E2 into adjacent side, which is A, divided by hypotenuse, which we already found out in the beginning, which is R square plus A square whole raised to 1 by 2. And we can write this equation as E1 plus E2 into A divided by R square plus A square whole raised to 1 by 2. So again, we are going to take the consideration that A will be very less than R. So what we obtain here is nothing but E net is equal to E1 plus E2 into cos theta, which we just reduced into the form A divided by R square plus A square whole raised to 1 by 2. Just so that you don't have any doubts, the image will be like this. Again, a point P will be here, plus Q, minus Q, point P. This will be the dipole and this will be the representation of that dipole, so that we know this is A and this is R. So we got this distance as A square plus R square whole raised to 1 by 2. And that is how simplify this into the form A divided by R square plus A square whole raised to 1 by 2. So we have reduced this equation into this form, and now we are going to substitute what we know for E. So we already know that E is equal to KQ divided by R square. Here R is again R square plus A square whole raised to 1 by 2. So we will write that as KQ divided by R square plus A square whole raised to 1 by 2. That is for E1. So this is E1. Similarly, for E2, it will be equal to KQ divided by R square plus A square whole raised to 1 by 2. That is equal to E2. Now, why are these two equal? Because the distance from here to here and here to here is similar. So that is why it is very similar. So now we are going to substitute E1 and E2, and now we can write that as, so we know that E net is equal to E1 plus E2 whole into A divided by R square plus A square whole raised to 1 by 2. And we just substituted E1 and E2. So we can write it as KQ divided by R square plus A square whole raised to 1 by 2 and plus again KQ divided by R square plus A square whole raised to 1 by 2 whole into A divided by R square plus A square whole raised to 1 by 2. Now we are going to simplify this equation and we got the answer. Now as you can see here, these two are common. We are going to take it outside and what remains in the bracket will be KQ plus KQ, which is 2KQ, and outside the bracket it will be A divided by R square plus A square whole raised to half plus R square plus A square whole raised to half, which is nothing but R square plus A square. So it will be R square plus A square into R square plus A square whole raised to 1 by 2. So this is whole raised to 1 and that is whole raised to 1 by 2. Let's say you have any quantity, let's say 10 raised to 2 into 10 raised to 3. So you can actually write it as 10 raised to 2 plus 3. So just like this, there is a power of 1, there is a power of half. So you just have to do 1 plus 1 by 2, which is 1 plus 1 into 2, 2, 2 plus 1, 3, 3 by 2. So this will be the power. So we can simply rewrite this as 2KQA divided by R square plus A square whole raised to 3 by 2. And now again we are going to consider the fact that A being very, very less than R, A can be neglected. So we are going to consider the fact that R being very, very great than A tends to be 0. So we can rewrite this equation as 2QA into K divided by R square whole raised to 3 by 2, and these two and this 2 will be cancelled. So we can write the final form of the equation as E is equal to, or E in total or E net is equal to, E total or E net is equal to 2QA into K divided by RQ. So we already know that 2 into A into Q is nothing but P. So we can write this as pk divided by r cube. So the net electric field at the equatorial point will be equal to, the net electric field at the equatorial point will be equal to pk divided by r cube. So this is the final equation for a point P which is at the equatorial plane of a dipole. So one thing you can actually observe here is that this is due to the equatorial point. This is due to the equatorial point, and when it comes to the axial point, E net was equal or was found to be 2pk divided by r cube. So we can actually assume that if a dipole, this is along the axial point and this is along the equatorial point. So the difference is actually that, so when we consider a point P at the axial points, then the electric field is 2 times more when compared to the equatorial points. So that is clearly dictated by the equations here. And the another fact is that if we are placing a single charge, as we go longer and longer, or the distance between any particles increase, then the electric field was falling by a factor of square. That is, the general electric field of a particle, let's say plus q or minus q, was given by kq divided by r square. So that as distance increased, it was decreasing by a factor of r square. But here you can see that as we move away from the dipole, the electric field strength is decreasing by its cube. As we move long distances away from a dipole, the electric field strength decreases by the cube of its distance. So that is again an observation found here. So these three are very much interrelated. So this is along the equatorial point and this is along the axial point, and this is for a single charged particle, either plus q or minus q. So let's summarize everything we have learned again. So we considered a dipole, and we considered a point P which was r distance away, and these two distances were A and A. So we found this distance to be r square plus a square whole raised to 1 by 2, and we found out that the electric field was E1 due to plus q was in this direction, and E2 was in this direction, that is inwards, and E1 was outwards because it was a positive charge and this was a negative charge. So due to a positive charge, the electric field was pointed outwards, and due to a negative charge, the electric field lines were pointed inwards. Since we cannot directly take this into account, we actually resolve this vector into its components of x-axis and y-axis, and we found out that the vertical components cancelled each other out, and the only remaining things were E1 cos theta plus E2 cos theta. So the vertical components, the sine components, cancelled each other out, and the horizontal components, which is the cos components, added itself, and we had this equation. And finally, we found the total electric field as E1 plus E2 whole into cos theta, and this was theta, and this also will be theta due to geometrical concerns. And we know that cos theta is nothing but adjacent side by hypotenuse. So we found this to be E1 plus E2 whole into adjacent side, which is A, divided by hypotenuse, which we found it to be r square plus a square whole raised to 1 by 2. And now we substituted the equation for E, which we already know to be E is equal to kq divided by r square. So here r is r square plus a square whole raised to 1 by 2. So we found that to be kq divided by r square plus a square whole raised to 1 by q plus kq r square plus a square whole raised to 1 by 2. When we add these together, half and half is equal to 1, and kq plus kq is equal to 2kq, and all of this was multiplied by A by R square plus A square whole raised to 1 by 2. So this equation simplified down to 2AQK divided by R square plus A square whole raised to 3 by 2. And now here we took the consideration that R being very greater than A or A being very less than R, we can directly write that E or E net is equal to 2AQ, which is nothing but P K divided by R square whole raised to, that is R square whole raised to 3 by 2, which is nothing but R raised to 2 into 3 divided by 2. These two will get cancelled out and we can finally say that this is R cube. So E net will be equal to PK divided by R cube. So this is an equation for the electric field of a dipole at the equatorial plane. So this is actually how we sum it up. So that is it in this class. We have learned about electric dipoles, how it behaves in the axial points and how it behaves in the equatorial points in terms of electric field. And we also saw that we can add electric fields using the superposition principle, and electric field is a vector quantity, so we have to resolve it into its components to add it. So that was all for today. I'll meet you all in the next class with more physics. Thank you so much.